We want to look at geometric random variables. Now, geometric random variables are used to represent experiments where we have independent trials, and each trial has only two outcomes: success with a constant probability of success for each trial P, and a probability and failure with a constant probability of failure for each trial 1 minus P. Now, it's important to keep in mind the random experiment might not have exactly two outcomes, but we should be able to classify the two outcomes as success or failure. For example, if we say success is head, then failure is not head, I tails. If in the case of a dice roll, we say success is 6, then failure is not 6, so all rest 5 numbers are classified as failure. So even though a dice roll has 6 outcomes, but we are able to classify them in the form of two outcomes, success and failure. Right? So the key idea is that you should be able to classify the two outcomes in the form of success and failure. So the trials are repeated in this case until first success occurs. So you don't have a fixed number trials like binomial, right? So you have independent trials, each with two possible outcomes, success and failure, and you repeat the trials until the first success occurs. So let's see how geometric is different from binomial. Now, just like binomial, in geometric, you do have repeated independent trials, each with only two outcomes. These are things that we looked at binomial as well, that you have independent trials, each with two outcomes, which you repeat. Now, in binomial, we had a fixed number of trials n, but in geometric, we don't have a fixed number of trials. We keep on repeating the trials until the first success occurs. So there are no fixed trials for geometric, unlike binomial. Now, the way we define a geometric random variable x is it's defined as the number of trials until the first success. Note the possible values x can take. Now, x can take all positive integer values. Now, keep note over here, because see, you might need to, you might get the first success in the first trial, you might get the first success in the second trial, you might get the first success in third trial, and so on. So, x can take all positive integer values. Remember, a binomial random variable can take a value 0, but a geometric random variable cannot take a value 0, as you need to perform at least one trial for success, right? Because it's a number of trials until first success, and you cannot get first success if you have 0 trials. So x takes all positive integer values, and it does not take the value 0. Now let's look at the PMF of a geometric random variable x. I want to see how do you find probability x is k. And probability x is k means, remember, x was defined as number of trials until first success. So x is equal to k means that k trials until first success. So the first success occurs on the kth trial. So we can write this as probability. The first is failure and second is failure, so on till k minus 1th is failure and the kth is success. Because when I say probability x is k, this means that the number of trials until first success is k. Right? So k trials until first success, the first success occurs on the kth trial. So here the first k minus 1 trial is a failure, and the last trial, i.e. the kth trial, is a success. We also know that each trial is independent of each other. Why is this important? Because we know when some events are independent, then the probability of the intersection, remember the comma means and intersection, right? The joint probability or the probability of the intersection can be written as the product of the individual probabilities. So we can essentially write this as probability first failure into probability second failure, so on till probability k minus 1 failure times probability k success, right? And this follows from the fact that we said that all trials are independent of each other. And the probability of success and failure is constant in each trial. So the probability of first failure is 1 minus p, probability of second failure is also 1 minus p, probability of k minus 1 failure is also 1 minus p. Right, so keeping these three things in mind, we can write this in this form: 1 minus pk minus 1 pk, because we know, given the fact that these are independent trials, we can write this as probability of first failure times probability second failure times probability third failure, so on till probability k minus 1 failure times probability k success. And then we know the probability of success and failure is constant in each trial. So the probability of first failure is 1 minus p, then times probability of second failure also 1 minus p, so on till probability of k minus 1 failure, which is also 1 minus p. So we're multiplying 1 minus p k minus 1 times. So we know we can write this as 1 minus p k minus 1, because repeated multiplication can be written in the form of exponents, right? And then we have, sorry, this is not k, pk, this should just be p, right? So this should be 1 minus p k minus 1 times p. The k here is a mistake, right? So probability x is k is just 1 minus p power k minus 1 times p, because only the kth is success, so this should just be p. There should not be a 3 on top of it, right? So the correct answer for this would have been probability x is k is equal to 1 minus p power k minus 1 times p, because only the kth is success. So multiplying with the probability that the last trial is the success, so it's just times p. You don't have k successes, you just have one success, right? Because the first k minus 1 are failure, so it's 1 minus p k minus 1, and the kth trial is a success, only the last trial is a success, so we just multiply the probability that the last trial is success, which would be p. There won't be a power k. Here, this is a type. So now notation for geometric random variable, we can write it as x is a geometric, in words, this means that x is a geometric random variable with parameter p, where p represents the probability of success for each trial. Now, how do we have formulas for expected value and variance of a geometric random variable x with parameter p. So expected value is just the reciprocal of its parameter p, and variance is just 1 minus p by x. Now, we have a very easy approach for finding probability x is greater than a and x is greater than equal to a for a geometric random variable x with parameter p. So if I want to find probability x is greater than a, what does x is greater than a means? That you need more than a trials for the first success. Because remember, the geometric random variable x is defined as number of trials until first success. So probability x is greater than a means that you need more than a trials for first success. Now this will be needed if first a trials were a failure. So probability x is greater than a is just 1 minus p power a, because it's the first trial is failure and second trial is failure and third trial is failure, so on till eighth trial is failure. Again, all trials are independent with the same probability of success and failure for each trial. So this just ends up becoming 1 minus p power a, right? So this is the probability that more than a trials are needed for first success, which would only be needed if the first a trials were a failure. So this is the probability the first a trials were a failure, which is just 1 minus p power a. Again, this follows from the fact that all trials are independent and the probability of success and failure is constant in each trial. An implication of this is that the CDF for geometric random variable can be written very nicely as fx we know is probability x is less than equal to a by definition of CDF. And using the complement rule, we can write it as 1 minus probability x is greater than a, and we know probability x is greater than a is just 1 minus p power a. So we can express the CDF for geometric random variable in this form. We can also find probability x is greater than equal to a very easily, because what this is saying the difference is here you need more than a trials for first success, here you need at least a trials for first success. You have to be careful about the difference between greater than and greater than equal to. It makes a lot of difference for discrete random variables. Probability x is greater than equal to a means that need at least a trials for first success. This will only be needed if first a minus 1 trials are a failure. So this just becomes the probability the first a minus 1 trials are a failure, which can be written as 1 minus p power a minus 1. Again, the way why we can write this as 1 minus p minus 1 is because this will just be probability first trial is a failure and second trial is a failure, so on till a minus 1 trial is a failure. We know all trials are independent, so we can write this joint probability as a product of the individual probabilities, and then we know the probability of failure in each trial is constant, so we're just multiplying 1 minus p a minus 1 times. Right, so for a geometric random variable, it's very easy to find probability x is greater than a and probability x is greater than equal to a, because this means that more than a trials are needed for first success, so first a trials are a failure. So this is just the probability the first a trials were a failure, which is 1 minus p power a. This is the probability at least a trials are needed. So this means that the first a minus 1 trials are failure. So there's a difference here. The first a trials were a failure, here first a minus 1 trials are a failure. So this is the probability the first a minus 1 trials are failure, which is just 1 minus p power a minus 1. And then we also have memoryless property, geometric random variable. It's the only discrete random variable with this memoryless property, which says that probability x is greater than a, given x is greater than b, can be simply simplified as probability x is greater than a minus.